Alright, so week 24, we're talking about sound. First of all, what is sound? Well, we've seen this before, so let's see. I'm gonna. Oh, this is not a video. Oh, poop. That's boring. If this were a video, what you'd see is the sound waves moving out like that, and you've seen this before. The little red X's indicate an individual air molecule, and they just move back and forth like this as the sound waves spread out. So the waves, sound waves going that way, individual molecule goes like this, so we call it a longitudinal wave, and it just has to do with the movement of air molecules. So that's what we talk about when we talk about sound. Our vocal cords are really good at producing sound waves of certain frequencies at certain times, which allows us to speak and sing and that kind of thing. So, standing waves in strings. We've done some experimenting with a slinky, and this is representation of the fundamental resonant frequency. So, fundamental resonant frequency. For example, a guitar string. So the guitar string is attached at both ends, and you pluck the string, and it moves back and forth and moves air molecules back and forth, and you hear that. When you pluck a guitar string, this is mostly what you hear. Is that so? This wave corresponds to a certain frequency, but there will also be a little bit of this and a little bit of this. And actually what gives instruments their characteristic sound is that because of just the structure of each instrument, they have different combinations of these overtones. So we can call this the fundamental, and these overtones, so this would be the second, we call this the first usually. This would be the second overtone, and this would be the third overtone. So maybe write that in. When we're talking about superposition, this is waves happening basically one on top of the other. So when the string goes back and forth, there's a wave bouncing back and forth and back and forth and back and forth and back and forth. And we get an antinode, region of maximum, right, and a node, region of minimum. When we have constructive interference, that is in this region, the antinodes. You might want to draw some arrows to those, and then destructive interference is where it cancels out, and that would be here at the nodes. Okay, what else do we need to talk about? Well, yeah, let's talk about this because it's related. So, if we look at the fundamental frequency, this is 1/2 of an actual wavelength. So I know we talked about this when we did the lab, but hopefully it makes a little more sense now. So when I write this formula, the length of the string is 1/2 the wavelength of the wave. That's the relationship between the length of the guitar string and the wavelength of the fundamental frequency. Okay, when we look at the second overtone or harmonic, the relationship between the length of the string and the wavelength of the wave is that they're the same. That's one complete wave. And then here, that's one complete wave, and that's another half. So we could say that the length of the guitar string is 1.5 wavelengths. Okay, so these are kind of important for what we're about to look at next, which is sound waves resonating in air columns. Alright, so here is a person playing the flute. The flute has an opening and an opening, and you blow over the top of the flute, and you can change the pitch that you hear. But basically sound waves resonate back and forth, back and forth, back and forth within the flute, giving it a characteristic pitch. What's happening, so we have two types of air columns. This is called closed because one end is closed and one end is open. And because it's closed, we don't have any movement of air molecules. Notice how there's a node and a node and a node, at the closed end. I would label that this end as closed and this end as open. Notice how there's an antinode, or maximum movement of air molecules at the open end. So again, this was closed, so these ends are closed, these ends are open. We also have the situation, as with the flute or sometimes organ pipes, when it's open at both ends. So we'd have antinode and antinode, and same down here and here. So you might want to label these as open and open. So let's talk about the frequencies and the formulas and stuff. So for the fundamental, we would have that the length is equal to 1/4 the wavelength. If I were to continue drawing this, it would be like there's half a wave, and it's going to be long. Let's see. And here's the other half. So if we break it up into fourths, it looks like that. Alright, so hopefully that made some sense. Here, so this would be the fundamental, our second overtone or harmonic, and third. So we have the length is 3/4 the wavelength, and here length is 5/4 the wavelength. What do we call this variable? That's right, lambda. So if this is the fundamental frequency, the next resonant frequency that this air column produces would be 3 times that, and then the next up would be 5 times that. Okay, and we'll practice with this a little bit. For both ends open, so maybe you're looking at this part of a wave that I've drawn and wondering what the relationship is between the length of the air column and the wavelength of the wave. You probably figured it out by now. The length of the air column is half the wavelength. And here, let's see, bottom to bottom, so the length is equal to 1 wavelength, and here the length is equal to 1.5 wavelengths. So bottom to bottom and then to top. So this is 1, and that's another half. Okay, so we have those relationships. So if this is the fundamental frequency, this would be twice the fundamental frequency, and this would be 3 times the fundamental frequency. Okay, 2 types of situations. Lastly, so this cool diagram is related to a lab that we will do. The question says, what is the speed of sound in air? And there's a tuning fork. We have a graduated cylinder. It's filled with water. And we're going to use a piece of PVC pipe that we can move up and down. And by moving it up and down, what we're doing is changing the length of the air column. And this end, because it's up against the water, is closed. And this end, because it's open to the air, is open. So what we're going to do, let's say that we used a C note, not a $100 bill, but a tuning fork that resonates at 262 hertz. And we're going to hold it over the air column, and we're going to move it up and down until the sound waves resonate, so they'll get louder. We'll hear an increase in volume. And let's say that we measure the length of the air column to be 32 centimeters. So we are talking about this type of a situation where this is closed at the water, this is open at the tuning fork. It would actually, well, it's up and down like this. Okay, open at the tuning fork, closed at the water. But this is what we're looking at, is the length is 1/4 the wavelength. So we just measured the length of the air column, to be 32 centimeters, which would tell us, so we know that the length of the air column is 1/4 the wavelength. So I'm going to use meters and multiply by 4, which means I'm going to get that the wavelength of the sound wave is 1.28 meters. So I know this, and I know that the frequency is 262 hertz. so I can find the speed of sound in air. This is kind of cool. Frequency times wavelength, or my frequency is 262 hertz. Wavelength is 1.28 meters. And I would get that the velocity is 335 meters per second. So we're going to get values similar to that. 343 is sort of textbook speed of sound in air at sea level, room temp, but that's an example of a calculation, so please know how to do that because we will be doing this in class. Lastly, this instrument, the didgeridoo, I had this super cool video, and then it wouldn't load. The internet's really slow. Let me see if Spotify plays these. Well, anyway, a didgeridoo is an open tube, and you blow into it, and because it's really long, there are these really long wavelengths, which means really low frequencies. So I will post this video of these didgeridoo players. It's about 5 minutes, and you'll see it on the website right below this one. You should check it out.